In this video, I want to have a look at something called the bisection method. So when we're having a look at polynomials, we often want to find where their roots are, or their zeros or their x-intercepts. And often we can do it algebraically if we can factorize that polynomial, but we can't always. If we can't do it algebraically, there's different methods we can use to approximate where that root is. And one of those methods, the one we're looking at in this video, is called the bisection method. So the bisection method is based on this idea here. If we've got a function, f of x, that's continuous for x values between a and b, if we find the value of the function at a and the value of the function at b, and they have opposite signs, so one of them's positive and one of them's negative, then somewhere in between a and b, we have to have a root of that equation. So for example, if we had our axes, and somewhere in there we've got a curve, our function, f of x, if we know that the value at this point b and this point a, the value of the function here is negative because it's below the axis, and the value of the function up here is positive, somewhere in between there it has to have a root, it has to cross that x-axis if the function is continuous. Just another example of what that might look like. If we have a function that looks like this is our f of x, we might have a value of a over here and a value of b on this side. So the value of our function is positive for a and negative for b this time, and somewhere in between there we have to have a root. Now it also says there must be at least one root. So sometimes there's more than that. So we might have a function that looks something like this. That's our f of x. Now we might have our value of a here, and that's positive, and we might have our value of b over here, and that's negative. In between there, we actually have 3 roots, not just one. Now, where the continuous is important is where this idea doesn't work is if we had an asymptote. So for example, if we had an asymptote coming down here, and then we had our function that looked like this. Now, if this was our a, the value of the function is negative there, and this is our b, the value of the function is positive over here, but there is no root in between there because of that asymptote. So this bisection method only works if it's continuous within that range. Now, if we have a look at how the bisection method actually works, there is a hint in the name. Bisect means to cut something in half. So if we have a look at this function, for example, we know that somewhere in between a and b, there has to be a root. So what we're going to do, we're going to find the midpoint of a and b. So we're going to find a plus b over 2, and we're going to find the value of the function at that point. So we're going to find f of a plus b over 2, and in this case, for the diagram that I've drawn, that value will be negative. So because that's negative, we know that the function now is going to be in that half of the interval, so it's now going to be between this value of a plus b over 2 and b. And then we can do it again, so we can find halfway between those. So in that case, it would probably be pretty much exactly on where our root is on this one. And if you end up getting a 0, you've found your exact root. But otherwise, you can keep doing this forever and get closer and closer and closer to where that root is. So you'll get smaller intervals each time. Often you'll be given a specific number of iterations to do. So it might say use the bisection method twice to find an approximation for the root. So let's have a look at an example. So our first example asks us to show that x cubed plus x squared plus x minus 5 equals 0 has a root between x equals 1 and x equals 2. And once we've proved that, then we're going to use the bisection method twice to find an approximation of the root. So to prove that it has a root, we need to substitute x equals 1 in and substitute x equals 2 in, and one of them should give us a positive answer and one of them should give us a negative. So if this is our function f of x, then we're going to find f of 1, which would be 1 cubed plus 1 squared plus 1 minus 5, which will give us minus 2, which is negative. And if we find f of 2, that's going to be 2 cubed plus 2 squared plus 2 minus 5, which will give us 9, which is positive. So we can say, therefore, there is a root in the interval between 1 and 2. So somewhere in there is a root. Now we're going to use the bisection method twice to get a smaller interval, to get a better approximation of where that root lies. So for our first iteration, we need the midpoint of 1 and 2. So halfway between 1 and 2 is 1.5. So that means we're going to find the value of the function at that point. So we'd have 1.5 cubed plus 1.5 squared plus 1.5 minus 5. And that would give us 2.125, which is positive. So we need our root to still be between this positive value and the negative value that we had before. So that means our interval now is between 1 and 1.5. So because this one was positive, we match it up with the negative from the step before, because we always need it to be between the positive and the negative values. So that's our first iteration. So we've made our interval a little bit smaller, but we want to get a more accurate approximation. So we're going to do this again. So now we're looking at this interval. So we're going to find the value of the midpoint of 1 and 1.5. So we're going to find the value at 1.25. So that's going to give us 1.25 cubed plus 1.25 squared plus 1.25 minus 5. And that would give us minus 0.234, and it keeps going, which is negative. So we now want it between this negative value and positive value before it. So we're going with the one that gave us the positive value. So that means our interval is going to be between 1.25 and 1.5. So our approximation is that our root is somewhere in between there. But we can also have a look and sort of figure out whether it's going to be closer to the 1.25 or the 1.5 by having a look at the value of each of those. So at 1.5 it was 2.125, so it was 2 units above the axis. Whereas here at the 1.25 it was negative 0.234, so that's much closer to the x-axis than this one was. So it is somewhere in this interval, but we can also guess or estimate that it's closer to the 1.25 than it is to the 1.5. If we have a look at what that function actually looks like, here I've drawn it up in Geogebra, and we're having a look to find the value of that root. So if I zoom in there, we have our initial that it was between 1 and 2. If I keep zooming in, you can see that it was between 1 and 1.5. And just keep zooming in further, you can see that it was between 1.25, which would have been about here, and 1.5. So that was our final approximation, was somewhere between here and here. And we did say that it was going to be closer to that 1.25 as well. That's having a look at the bisection method for approximating a root.